So good morning, everyone. We shall continue our lectures. This is chapter 3, where I will talk about a statistical description of turbulent flows. So now we are going deep down the topic here. There will be some equations, some mathematics, statistics, fundamentals of turbulence in this chapter, but there won't be much Navier-Stokes or transport equations. They will come in chapter 4. But in this chapter, that's the bedrock of building the arguments around turbulent flow and setting the stage for what's going to follow next. If you look at the Navier-Stokes equations, which we showed you last time, these equations are deterministic, which means that you can solve them exactly if you have the right computer. Or in the simple cases, you can actually solve them by hand, analytically, if they are simple. So they are supposed to give you an exact answer. But that's not what happens in reality in a turbulent flow. If you look at the velocity field u, and we talked about u as being a vector, is a function of position vector x and time. We claim this to be random, despite the fact that the Navier-Stokes equations are deterministic. So that's bizarre. We did not expect this. Why did this happen? In other words, if Navier-Stokes equations are prognostic in a sense that they are developed to be predictive, I mean, we develop the Navier-Stokes equations to make some prediction. But we can't. The question is why? Here's the answer. In any turbulent flow, there are unavoidable perturbations in initial conditions, boundary conditions, and material properties. So last time we did talk about perturbations as the essence of turbulent flows, in the sense that there are the perturbations that grow and amplify. So a flow becomes eventually unstable and turbulent. So the perturbations will be there. So that's the cause of the problem. But what do perturbations do? Well, in turbulent flow, the equations show a very acute sensitivity to such perturbations. And that's why there are still deterministic equations, but they go crazy, if you like. They go wild. Any perturbation, fluctuation, instability grows, and the equations that predict chaos, actually. Okay? It's still deterministic, but it doesn't have much useful predictive power. See what I'm saying? So it's the nature of the physics. There's nothing wrong with the equations. Equations are right. But it's just the nature of physics that causes the flow to be random. And I can demonstrate this using a very nice example. I like to call this the golf ball trajectory example. Who likes to play golf here? Yeah, Scott does. I've tried golf too, but the indoor version. So the mini golf. It's really fun. If you think about it, if you play mini golf, right, so the hole is right in front of you and you just sort of swing the club very gradually, you can actually pretty much guarantee that the ball will go in the hole. I mean, if it's like half a meter away and you have sort of control over your arms and swing, you can do it. So what happens in real golf? Can you determine that the ball will go in the hole? No. It lands like meters, if not kilometers away, usually. Well, why so? It's the same game. Why is mini golf so different from actual golf? You might think of the scale of the game is now much bigger. And you can actually tie this into what I just told you, perturbations. In real golf, there are many perturbations. Think of it. When you send the ball up, there's wind. You don't have control over the wind. One might blow in one direction, and seconds later it might go in the other direction. So it actually takes the ball. The club you swing has imperfections on the surface. Maybe the angle is not perfectly what it's supposed to be. There is a tolerance there. The way you swing it, if you sort of start with the wrong angle or power, then this deviation amplifies a couple hundred meters down your location. All of these things multiply. If there is topography is complex, there's a lake, there's hill, there's temperature perturbation. So all of these perturbations add up. So eventually you cannot determine where the ball goes. Okay, so this is an analogy. If you want to think of it, mini golf is like laminar flow. There's no perturbation. Even if there are, they are going to be damped, and the effect will be gone. But real golf, these perturbations amplify and grow into instabilities. I can actually do a sketch for you too. Just put a picture to what I just said. So golf example. If you play mini golf, so indoors, this is probably Scott. He's holding his club here, and then there's so the hole is just a few centimeters away. So here's the hole, here's the ball. Swing his club, the ball goes right into the hole. So in this sense, any perturbations are damped. So this is like laminar flow. Real golf so it's can be complicated. Well, first of all, the topography can be complicated. So here you might have some forest. Then there's water bodies. This could be a lake, forest. There might be a ramp, and maybe eventually the hole is here. Here's the flag. So you swing the club. The ball goes up, but then at that point you have no control of what happens next. There could be perturbations in the wind, or temperature or pressure. The ball may even hit a couple of points, right? Bounce off a couple of points, and every time it's going to be deviated from where it's supposed to go. So in this example, we could say any perturbations are amplified this results in instability, which is like turbulent flow. Okay. So because this happens, we think of u, or velocity, as a random variable, which means if you swing the club and let the flow evolve, there's no guarantee what velocity will be at a given time and space. It will be unpredictable. It will be some sort of a random variable. Okay, so you cannot predict exactly what it will be, but the hope is that you can predict some of its statistics. For example, you cannot predict it exactly, but can you at least determine its mean and standard deviation? That's what the statistics does. If you have a lot of variation or work with a sample of numbers, then a statistic will help you draw some conclusions on the sample of numbers. Some things like mean, standard deviation. There's other statistics you can calculate. You could do skewness, kurtosis, and the list goes on. But mean and standard deviation is the most important ones. Okay. So now we are going to switch gears and give you a mini lecture in statistics. And I have to say statistics are important in turbulence because we derive and develop equations, we analyze the system using the statistical concept. So you really have to like this and get good at it, which many of you are, I would presume. I want to define mean or average, if the loose term. Well, I could sort of define by saying, okay, you have a bunch of numbers, add them up, divide by the number of measurements, and this would be mean, taking an average. But I'm not going that route. I'm going to take the statistical approach, which means I start with the probability distribution of some event. Many of you have seen this, that any phenomenon that happens and it's random in nature has a probability distribution. This might sound familiar. Probability distribution always varies over a large collection of possibilities. Imagine v velocity could be anywhere from minus infinity to positive infinity. So these are all the possible outcomes, but you expect this to be concentrated or more likely to be around, let's say for this flow or this density function, around the average mu, which in this case happens to be 0. The density function also has a standard deviation. We use sigma. Many of you have seen this as the normal distribution or the Gaussian distribution, but it could be any shape. It could be flat, it could be chi-squared, it could be, there's many different types of distribution. So you have some sort of density function that gives you probability of velocity for being a particular value. The mean of a random variable u, or velocity, can then be defined as taking the integral of this density function multiplied by the velocity. Imagine that you have the density function, you integrate it from minus infinity to infinity. That gives you the mean of the velocity. And this symbol, the angled brackets, in this course we use to represent mean. In other courses, you might use the overbar. You put an overbar on a symbol, that means mean. But in this course, we use the angled brackets. So you have a probability density function, a PDF. You know it as f of v. You've also seen the cumulative distribution function, CDF, where you obtain by integrating v from minus infinity to a given point. So again, I'm not going to go too deep in the statistical definitions. We have these defined in the appendix for you. And in general, you can calculate any statistical quantity you're after using this type of integration. So if I give you the probability density function, you can calculate many statistical predictors, like mean, standard deviation, and so on. In fact, more generally, if you have any function of velocity, like u, function q of velocity u, is any function, then the mean of that function can be obtained by multiplying that function by density function and integrating it from minus infinity to infinity. In a bit, I'll show you how you can do this for standard deviation as well. It's the property of integral that is very linear. It is a linear operator. Let's say the mean of two functions, sum of the two functions, is sum of the means of the two functions. Right? So mean of, let's say, q plus r is mean of q plus mean of r. Even if you have multipliers like a and b, these could be fixed numbers. The mean of aq plus br is a times mean of q plus b times mean of r. So this type of, the integral is an operator. It's like adding two numbers is an operation, right? Multiplying two numbers is an operation. It's a mathematical operation. Taking the integral is also a mathematical operation. That's why we call it operator, the integral operator of this sort. And I'm just telling you it's linearly, it's a linear operator because if you have any constant inside the integral, it jumps out, right? Also, integral of two functions is just integral of the first function plus the integral of the second function. So it's just the property of integrals that they are very linear. Now I will define standard deviation for you. The first concept I should tell you is this. If u is a random variable, like anytime you measure it, it's something different. It is useful to subtract the mean from it and only consider the fluctuation or the deviation from the mean. So remember, mean is now a fixed number. After I find the mean, it's some fixed number, like 5.5 meters per second. If I subtract this fixed number, which was the mean, from the random variable, I get by definition the fluctuation, which itself is a new random variable. And we call this fluctuation of u, and we show it with little symbol u. So fluctuation of u. Then its variance, if I define a new function, think of it, I just told you I could have any function q. If I take this deviation, little u, raise it to the power of 2, then I can have a new function. Think of it this way, I just told you. So q is, here q is I just define it to be the fluctuation to the power of 2. I just define it to be as such. If I apply the integral operator to this fluctuation squared, then I get the mean of the fluctuation squared, or mean square fluctuation. this we know as variance, and if you take the square root of the variance, you get a standard deviation. And you can show that by mean of fluctuation squared under the square root. And this is not any different from the basic knowledge of the statistics you have, right? Any sample distribution. When you talk about variance, you're talking about a fluctuation away from the mean of some random event. And you calculate its mean of its square, its variance. If you take the square root, it's standard deviation. It's the same definition. Nothing new. I will give you a very sensible example. Suppose velocity is a random event and you measure velocity 6 times. And you measure 1, 2, 3, 3, 2, 1. So these are some measurements of velocity in meters per second. Average of this is 1 plus 2 plus 3 plus 3 plus 2 plus 1 5 or 6. The average is 2, or the mean is 2. The fluctuation is u minus the average, or mean of u, and itself is a sample. If you take 2 out of the values of u, you get this vector, which is now little u, or the fluctuation. I can also give you a visual representation of this, which is not difficult to do, so I'm going to rotate my notes. Suppose you measure u as a function of time. So if you measure, I told you, you're not going to get a fixed number. This u is random. The average of this you can represent by a line. If you take the average of all of these numbers, you get average u, and then fluctuation would just be the difference of, at any point, the difference with this average. So this, on that location, this is u, small u, probably larger than this location. Right? So this u itself is a random, the small u is a random variable, and it will vary depending on the value of u. So back to our equations. In the same fashion, you can find this. Oh, this was a V, by the way. Up here had a V. Let's just do the definition work nicely. It was a V. If you find this fluctuation and raise it to any power, here we raised it to the power of 2. But it doesn't have to be 2. You can raise the fluctuation to the power of 3 and then take the integral. Power of 4, take the integral. If you did that, you would be calculating the nth moment, or central moment. If n is equal to 3, then this is called the third central moment. In basic statistics, we know this as, what do we know it as? In the statistics? Skewness. If n is equal to 4, I said it earlier, if you were listening, kurtosis. And you can go all the way up. But we seldom do in turbulence. 2, 3, or 4 is as far as it goes. Okay, so same definition. And we should use the symbol mu. Please do not confuse this with viscosity. Viscosity, this is just moment. I'm going to skip this next subheading because you should be familiar with it. You can standardize the random variable. If you divide this by the standard deviation, then you get a standardized random variable, and you can get a standardized moment. So if you open any textbook in statistics, they give you a table at the end for the standardized Gaussian distribution, which the mean is always 0 and standard deviation is 1, right? And then you use that, from that you can go to any arbitrary Gaussian distribution, because that distribution has been standardized for the use in the textbooks. You can go from that to any other arbitrary distribution. The mu or average could be anything. It could be 2, 3, 5, 17, minus 6. Standard deviation 2 can be anything. 1 to 10 cannot be negative. It's just a way of dealing with it in a useful sense. So I'm not going to discuss that. It doesn't really take to us very much. But for the sake of completeness, I put it in there. Skewness will tell you how is this probability distribution function is shifted sideways, how asymmetric it is. I mean, a Gaussian distribution is perfectly symmetric about the mean. Like on the left hand of the mean, you get the exact mirror image of the right hand. But imagine you stretch this Gaussian distribution so it's asymmetric. This is when a skewness comes in, right? If for a perfectly Gaussian distribution, skewness is 0, it has no sort of stretch or asymmetries with respect to the mean. But the more the higher the skewness, the more skewed the distribution will be. Kurtosis is known as flatness or tailedness. How far the tails of a distribution go. So the more the tails of a distribution persist, the higher the flatness. But if the tail dies out to 0 very quickly, kurtosis is very small for 0, something like that. So just keep that in mind. So these extra statistics explain the shape of the probability density function. Before I discuss the joint random variables, I'll just put some symbols up here because we're going to use them. So we talked about U, V, and W. Capital case U and V, W. Now we're going to talk about lowercase u, V, and W. And these are now fluctuations. Okay. So in the Cartesian system, you got X, Y, Z. The velocity fluctuation in the x direction is little u. Velocity fluctuation in the y direction is little v. Velocity fluctuation in the z direction is little w. And these are arbitrary. I mean, for this room, this could be x-axis, this could be y-axis, and then this could be the z-axis. Right-handed, x, y, z. Fluctuations that happen in the air in this room could have a component in the x direction. I know it as little u. Component in the y, I know it as little v. And fluctuations in the z direction, component w. I mean, I could think of them as u1, u2, u3. Same thing. I'm just saying 3 components. You should not be confused. But they mean the same thing, 3 components. Now, it gets very exciting when you get to joint random variables in turbulence. And these are based on joint probability density function. We call them JPDF because these density functions are now two-dimensional. The Gaussian curve, as we know it in any basic statistics course, is defined over one dimension. You only have one random variable u. But there is two-dimensional Gaussian distribution, which is a surface over two random variables x and y. Right? This we know as a joint probability density function. And this defines the likelihood of a pair of events to happen. Let me give you a sort of a funny example. I want to know any pair of students in this room. I want to know if their age, what is their age difference. I need two variables here, right? If I pick myself and Arash, I mean, you're much younger than I am, right? So this age difference between you and I is a large number. But if you take you and Shen, another pair of variables, the age difference is smaller. So you see, this is kind of a joint probability distribution. There are many possibilities. I can take you and myself, you and Chen, you and Scott. What's your name?
David.
You and David, you and Ragul, right? So that's all the combinations with you. Then I can get Ragul and me, Ragul and you, Ragul. So you see, every pair of random variables have some outcome. So this we know as joint probability density function. And any function you want now depends on, the density function depends on two variables, v1 and v2. For turbulence, these could be velocities, like u and v, or u and w, or v and w, any pair of velocities. The covariance of u1 and u2, or u and v, is the mixed second moment and can be expressed using the PDF by this formula. Remember I told you we have variance, which is only one fluctuation to the power of 2 variance. Covariance, I need to multiply 2 fluctuations together. So I use this symbol. So covariance is the mean of the product of 2 fluctuations in different components of velocity. And then to evaluate this, I have to take a double integral. In this case, my arbitrary function is now q, a function of 2 variables, u1 and u2. I have the density function f12, which is function of the 2 components of velocity, and then I have 2 differentials here because a double integral is integral over an area element. Okay, so that's all fun. Covariance. And in fact, you can normalize this covariance into what we know as correlation coefficient. If you divide this covariance by the product of the individual variances of each component and take the square root, you get a normalized correlation coefficient, which is always between 1 and -1. And that's the very reason we normalize it, because we want to bound it between 1 and -1. And here 1 and 2 are the subscripts. I'm just telling you I want to calculate correlation coefficient for component 1 and component 2 of velocity. Give you some sensible example. For example, you can calculate many of these correlations. You can calculate covariance of U, V, U, W, and V, V, W. There are three possibilities. Or if you want to use the component form, you can do U1, U2, U1, U3, and then U2, U3. Same thing. And I have a very cool picture to show you. That's the next page, which shows what I mean by this covariance or correlation coefficient. Now, if you normalize, if you take two variables, if they are exactly, the fluctuations are exactly opposite to the other one. Let's say one velocity, whatever it is, the fluctuation is 1 meters per second. The other one is exactly opposite, minus 1 meters per second. If this one is 2 meters per second, the other fluctuation is minus 2. If this one is minus 3, the other one is 3. If they're exactly opposite in sign, same magnitude, then I get a correlation coefficient of minus 1. Remember, this variable represents U1 with respect to U2, if you like. And you get, so this is the 0 point, if you want. See what I'm saying? If they're exactly correlated, that every time you measure these two pairs of fluctuations, they're both positive or both negative, then you get a correlation coefficient of 1. But you could get sort of mixed states in which they could be almost positively correlated or almost negatively correlated, or the correlation could even be lost. Like in this case, the correlation coefficient is 0. Statistically, there is no relationship between the two variables. Let's say I measure velocity fluctuations U in this room, and I simultaneously measure velocity fluctuations V in the next room. There's no reason why these fluctuations should be correlated. The correlation coefficient should be 0. But if I measure both of them here at the same location, then the flow in this room is sort of part of the same continuum that all of these components are related. A very nice concept. Now, let's go back and finish the last page. Normal and joint normal distributions. When I say normal, I mean the same thing as Gaussian. This distribution was discovered by a German mathematician, Gauss, Carl Gauss, I think. So he was the grandfather of random processes. I mean, when you say random, you use it in a very imprecise way, day to day. Like, if you talk to this random guy, or if, But in mathematics, random means something very special, okay? Which is this: only if the density function of some event is normally distributed, only then is a process or fluctuation random. If it's not normally distributed, it's not random. You see what I'm saying? So not any type of chaos is random. Only certain types of variations are random. It's a very profound concept. And we've seen in most statistics books, there's some variable x, then here's the distribution. It's like a bell curve. The average is mu. Standard deviation is sigma. We show standard deviation sort of as a width. I mean, this could be narrower or could be wider, in which case sigma would vary. All of them qualify for the normal distribution. The next concept I should talk about is the concept of ensemble average. If turbulent flows are exhibit some randomness, the only meaningful way to measure and report something in this flow is by doing some statistics, right? So you need to do some averaging to make any useful statement about this flow. One type of average is called the ensemble average. Assume U is a component of velocity at a particular space and time in a repeatable turbulent flow experiment. That means this flow happened and I measured velocity, a velocity component somewhere and at some time in this experiment. And I repeated that measurement. I repeated the whole experiment. I didn't continue the same experiment. I repeated the whole experiment from the beginning. Then UN denotes the nth repetition of the experiment, i.e. coming from another measurement of U. Then the set of random variables that come from different experiments, U1, U2, U3, and UN, if you did this measurement n times, should be independent and must have the same distribution of U. So these are independent, identically distributed. Then the ensemble average is calculated by, I'll give you a very nice practical example in a moment. The ensemble average is calculated by this, and you've seen this before. It's like a very basic way of taking average. I'm not using integrals and PDFs. I'm just saying take the average. This is called ensemble averaging, and we use the symbol suffix n, right? Pay attention to n. This is excellent material for an exam problem, right? N is ensemble average. But this was not an ensemble average. This was just mean, right? Calculated using mean, calculated using probability density functions. These mean different things. Okay? Now, what is ensemble averaging? There was something I talked about. I have to repeat the experiment. It cannot be the same experiment. So I brought these from my office. I'm a fan of ping pong. Who's a fan of ping pong? All right? Okay. I I want to throw this ball, ping pong ball, to Arash. And I'm interested in velocity right here when the ball reaches here. I'm interested in its velocity components, u, v, and w. Of course, if you play this game many times, this velocity won't be the same. You agree? Because there are perturbations. I swing my racket in different ways. The air, perturbations, temperature, things change. So I have to repeat this game maybe 100 times. And each time I have a new experiment. It's an independent experiment. It's not the same experiment, right? And then I add all these numbers, velocity components up here, and then I calculate my average. So this is experiment 1. Are you ready? So that was one experiment. And you could measure the velocity over there. So the next experiment. This experiment is independent. Do you agree? I mean, what happened before has no influence to what happened in this game. That's second experiment. Now I have 2 experiments. They should be independent, right? 3 experiments. And the game goes on. So thank you very much. I just wanted this, I want you to remember this, right? It's such a profound and important concept here. When you do turbulent, develop theories of turbulent flows, you have to repeat the experiment. When you say ensemble average, it means that you had a flow system and you cranked it up from the beginning, the flow evolved, and then you made a particular measurement at some point in time. For the Archimedes screw, it would be pretty harsh to ask you to do it, right? That means start the screw, run the experiment, pump the water, wait 5 minutes, and exactly at 5 minutes, measure velocity here. Turn the machine down, right? Repeat one full time, and probably you will never graduate if I asked you to do that. But the theory is developed for the ensemble averages. We'll get into complications in real life. And you can use some theorems in statistics to show that the average of the ensemble average is the same average as the mean calculated by PDF. But the standard deviation of the ensemble average itself is going to be lower than the standard deviation or variance of the original distribution. In other words, the more you repeat the measurement, the closer and closer values you'll obtain. You think of it this way: Arash and I can play this ping pong game 10 games. That's one average. That's one random variable. Finished. Like U1 of 10. Then we play another 10 games. That's another measurement. Then we play another 10 games. So you can think of these ensemble averages as being random variables themselves, which they, in their own right, they have a mean and a standard deviation. I'm just relating the mean and standard deviation compared to the original distribution. By the way, which I never know. The beautiful thing about statistics is you have no idea, you will never know the true mean. Let me put it this way. You never know this. What's the PDF? Nobody knows. It's just a mathematical concept. Because you cannot repeat this experiment infinite times, you run out of time. Right? All we can do is ensemble averaging. You don't know the true variance, standard deviation, but you know it's related if you repeated this experiment. It's a very profound concept. In the limit of an infinite number of measurements, Arash and I played this for years here, ping pong game, if the ensemble average is calculated over a very large sample, then the standard deviation actually can approach 0. Right? So you can sort of play the role of a tough guy. Just measure and measure and measure and measure and measure 1 trillion times. Then you would kind of close the gap on the variance of our standard deviation of this experiment, but not practical. We can, by very few number of measurements, we can draw a useful conclusion. We don't need a million, but maybe 10, 20, 30, we can draw some useful conclusion. Okay. And, I mean, here is another piece of information on central limit theorem. There's another powerful theorem that he said if you repeated this experiment, then the distribution for the repeated experiment will approach a Gaussian distribution. So by a game of repeating an experiment, you eventually convert any process into a random process. You know what I'm saying? Like this ball, for any moment I throw it, could not have been random. That does not necessarily need to have been a random process. It could, maybe did not follow the Gaussian distribution. Let's say a velocity component of it. But if I played this game many, many times, the ensemble average then had the shape of, was distributed according to the Gaussian distribution. So ensemble averaging is related to forcing a process to become random. It's a very profound concept. Okay. So let me underline this. It really deserves to be underlined. So it is an important result, indicating that regardless of the nature of fluctuations, i.e. they could be expressed using any other probability density function, the standardized fluctuation of ensemble average random variable will have a Gaussian or normal form. Sounds like a math lecture. And it is. I mean, fluid dynamics is math. Anything is math, if you ask me. Random process. So if you got worried about the Archimedes screw, yes, it's not possible to repeat an experiment in order to, infinite times in order to obtain ensemble averages. Sometimes even flows do not repeat themselves, especially in environmental flows. The atmosphere changes minute by minute. I can never have the same day twice, right? Or the ocean changes all the time. Even Archimedes screw changes all the time. Like power fluctuates in the building, temperature changes, equipment wears out, water temperature changes. Never, in fact, in the physical world, it's never possible to repeat any experiment. You only live life once. So what do you do? In those cases, it is useful to develop theories for the same experiment, but only as a function of time. I mean, yeah, it's a next level of approximation. You can't repeat an experiment, but over time you can assume it repeats itself. That means if you turn on the water on the system, you just let it go and assume it's the same experiment in time, and you keep a measurement at some point, do it for 5 minutes, and then that's your number, and then you're averaging based on time measurements. For instance, velocity as a function of time is one of those things. It's a much more practical way to deal with a random process. So you assume that the time-dependent random variable is called a random process. Many random processes are statistically stationary. So that's a new term. It's stationary if all multi-time statistics are invariant under a shift in time. Which means that if you measure, let's say, air velocity in the x component in this room for 5 minutes, calculate some ensemble average of air velocity, 5 minutes. I finish that experiment, I continue the same, another experiment in time. Measure for another 5 minutes the velocity fluctuation in u. And then measure for another 5 minutes. If the number I calculate at the end does not change, this process is a statistically stationary process. That means if time changes, your statistics are not going to change. Stationary, I mean, not the best choice of words because stationary has to deal with statics, but we are using it in a sense of time. It's kind of bizarre, so please don't be confused. So statistics don't change. Statistically stationary. For a statistically stationary process, the simplest multi-time statistics is the autocovariance, given by this symbol. By the way, if it's not electronic mathematics, in the labs you actually calculate all of these using turbulence data. So when you do the labs, computer labs, all of these definitions will settle in place for you, hopefully. So we calculate all of them in actual experiments. For a statistically stationary process, the simplest multi-time statistic, I say multi-time because the measurements are happening at different times. I put a sensor here, it measures something at different times. It's a multi-time measurement. I could have some other possibilities, like multi-space, single-time measurement. For example, think I could measure velocity at 2 points simultaneously. This is not a multi-time measurement. It's a single-time multi-space measurement. Okay, so, but now we're talking about multi-time measurements at the same location. And we call this autocovariance, which means that measure some fluctuation at some given time, and then measure it later, and then calculate the covariance of it. You can do it. I'll give you some specific examples. This autocovariance is not a function of time anymore itself. It's just a function of time shift S. You know what I'm saying? If the flow was statistically stationary, nothing should change with time. Any statistics I calculate, if I calculate now, if I calculate a minute later, if I calculate 2 minutes later, it should be the same. So time is not a question here. It's the shift in time that gives you the autocovariance. So the flow is measured at the same location with the time shift S over an infinite time period. You could normalize this capital R and obtain the autocorrelation function, which we use rho. Again, this rho should not be confused with density or correlation coefficient. This rho is known as autocorrelation function. And you obtain that by calculating the covariance of fluctuations with time shift divided by variance of the signal measured, which could be the fluctuation. And we defined this for you already. The nice thing about this autocorrelation is that any signal is 100% correlated with itself at the same time. Right? I mean, for example, my velocity right now is 100% correlated. At that moment I was walking at 0.5 meters per second. I was 100% correlated with myself. But my velocity changes with a time shift. For example, I have no velocity now, and a second later I have some velocity. See, the time shift has some implications. Now, the closer the time shift to 0, the more I'm correlated with myself, right? My behavior is instantaneously the same. But the longer the time shift, the less I'll be correlated with myself. I mean, if you think about a millisecond, I'm pretty well correlated with my velocity, right? A millisecond time shift. But if you compare my velocity now and in the afternoon when I'm sitting in my office, there should not be any correlation. I mean, the time shift is so large, the gap is so wide, there's no guarantee that I'll be walking with the same velocity. So, our correlation function at a time shift of 0 is pretty much 1, but for other time shifts it's always less than 1. Maybe 0 at a very long time shift. I can give you again a visual representation of this. Autocovariance I'm interested in some signal fluctuations, so small u is u as a function of time minus the mean of u. I want to know how is it possible to measure this. I mean, in a real world sense. I want to measure autocorrelation for air fluctuations, air velocity fluctuations in some given direction, x, y, or z. How would I do it? There is a sensor out there which is called a sonic and ultrasonic anemometer. Ultrasonic anemometer. So let me spell it out for you. Ultrasonic This sensor measures U, V, and W at high frequency. And we have actually many of these ultrasonic anemometers in the engineering building. Like we have maybe even 10 sitting around. So if you do atmospheric research and you need one, come ask us. Pretty cool. So it gives you 3 components of velocity at a very high frequency. If I want to measure our covariance for a fluctuation of air speed in a particular direction, I could use one of these ultrasonic anemometers. Let's say I bring you to this room. I bring the ultrasonic anemometer, I'll bring you to this room. And then I create a flow condition. I mean, let's say I could start a fan in this room and create flow coming toward the ultrasonic anemometer. So I could bring a fan here if you like. So blow the fan, and then it brings wind toward the anemometer. Well, x is the direction of the flow. I mean, for u, I could imagine y be normal to the page, and z be away from the surface of, or the bottom floor of the room. Suppose the flow is going to be turbulent, and it must be, because otherwise there's no fluctuation. It will be 0 all the time. So I want to assume a statistically stationary condition. If it's a statistically stationary, the flow that approaches me is the same, has the same behavior. Let's say there could be an eddy that's formed by the fan, a turbulent eddy that's formed. It just keeps coming forward, and then it comes here. Then the next eddy is formed. Then the next eddy is formed. Then the next eddy is formed. So see, the flow is statistically stationary. These eddies should not change substantially. I couldn't make an eddy and then no eddy. Or I couldn't make an eddy and then eddy twice the size. So constantly these eddies, the same size and velocity and other characteristics should come my way toward the anemometer. Let's say this eddy is some time shift s with the next eddy, which means if I'm standing here, I'm the anemometer, one eddy comes and passes me, right? It takes s time shift for the next eddy to come. Every time shift s, one eddy comes and passes over my probes. So they're only s seconds apart from the point of view of the anemometer. Okay? For me to calculate the correlation coefficient or autocovariance, I should calculate the ensemble average of fluctuation for every pair of these eddies. You see what I'm saying? So probably I should put my sensor there and wait half an hour, and I measure a bunch of them that are only one s apart. So this would be R of U, R of S, which is U at any time plus U at time plus time shift S. I can measure many different autocovariances. What if measuring covariance of fluctuations that are 2s time shift apart? That's possible, right? That means I'm calculating the covariance for longer time shifts, time delays. If I did that, I should then do it this way. Measure this eddy when it's here, and then measure the next time I measure is here, or if these eddies are going downstream. What's the next measurement? Is it from here to here? No, I can actually, there are many combinations of eddies that are 2 time shift apart. You see what's happening? Any of these could qualify. So I have a lot more combinations and pairs to work with. You see what's happening? I calculate some sort of a mean for different pairs. I could calculate the autocorrelation function for even a longer, or autocovariance function for a longer time shift, 3s. If I did that, then I'll be looking at eddies that are sort of 3 time shifts apart. Okay, so that's what we mean by autocovariance. You calculate the covariance of a signal with itself for different time shifts. Oh, by the way, this was an eddy. And if the flow is stationary, whatever S you choose, doesn't matter for how long you do this measurement. If you do it now, if you do it 2 minutes later, you calculate the same autocovariance. And then you normalize it. plotted. If you normalize the autocorrelation, it's a function of rho, it's a function of time shift. So that's the y-axis. The horizontal axis is s, or time shift. If there's no time shift, what's the autocorrelation? 1. The example of a signal is 100% correlated with itself at any time. But the longer and longer the shift is, the correlation should go down, right? Eventually, it should, I mean, theoretically speaking, it should get very close to 0. It could also be negative. I mean, it can happen. But we are mostly interested in this region. I mean, close for a small time shifts. If you take the integral, of this autocorrelation function with respect to time shift from 0 to infinity, this means the area under this curve, if you calculate that, we know this as the integral time scale. And this integral time scale has a very significant physical interpretation, which I'm going to define for you. You have it down? Notes. So integral time scale is the integral of the autocorrelation function over time shift, and well, for most, at least theoretical flows, it should converge to some number. If you take this integral, it should be some number, 5 seconds, 3.5 seconds. Remember, it's a time scale, so when you do that, the units should be time of the integral. Now I want to tell you what it is, physically speaking. Physically speaking, what is tau, or the integral time scale? This tau, or integral time scale, looks at the overall memory of the process and how strongly it is influenced in or correlated by a state of flow in previous time. Okay? That means the flow is more correlated with itself if this number is large. If this number is small, the flow is not correlated with itself. It changes way too quickly. I'm going to use my walking as an example. If I walk in this fashion, I am very highly correlated with my velocity at the previous state. Right? The integral time scale for my movement is maybe 5-10 seconds. What if I do this? What's happened? I very too quickly change my velocity. The integral time scale for this type of movement is much small, maybe half a second, if not quarter of a second. So you see what's happening? Flows can do that. If the nature of fluctuation sort of remembers itself, slowly varies. One eddy comes predictably, and then the next eddy comes, and then the next eddy comes, and then the next eddy comes. then you have a high integral time scale. But if eddies like burst in and out of existence, they quickly disappear, then the flow has no memory or very little memory. You can even try it outside. Go out there in a very gusty day, right? Stand there, you see these bursts of wind coming to your face. That type of flow has very little memory. These bursts come and go. But if you go stand in front of a breeze, what happens, right? It's much slower eddies, more consistent eddies coming away. So flows can do that. When we talk about integral scale of the flow, we are talking about the memory of the flow, how well it's correlated with itself at a previous time. Okay? And again, do you calculate all of these things in your computer assignments? There's lots of turbulence data sets, and you will calculate these integrals scale. Let's see if there are any questions. Sounds good? Okay, so we'll see you next time.